Hello and welcome to Chapter 9. In this chapter, we're going to talk about Venus. This is going to continue our exploration into the individual planets. In our last lecture, in Chapter 8, we talked about Mercury. We also talked about the Moon because of some similarities between Mercury and the Moon. But that was our first planet discussing Mercury. We talked about its unusual elliptical orbit, about its very unusual day, and how close it is to the Sun, and having no atmosphere and a weak magnetic field. Well, what are going to be the takeaways from Venus? Are we going to learn similar rules for this planet? Yes, we certainly are. So let's get to discussing Venus. All right, we're going to talk about the orbital properties, the physical properties, long distance observation of Venus and why it's so difficult. All right, very, very difficult stuff. We'll talk about the surface of Venus because we do know some things about the surface of Venus through hard work and study. We'll talk about the atmosphere of Venus, which is a hot topic about Venus, literally, and pun intended. And we'll talk about Venus's magnetic field, or lack thereof, and its internal structure, right? What do we know about it? Okay, well, let's get on to talking about the orbital properties of Venus. Okay, well, it's much brighter than Mercury, all right? And it can be further from the sun, all right? And so, I mean, it's in its orbit, it is generally further from the sun than Mercury is, okay? It's called the morning or the evening star because, like Mercury, it's tied to the sun. And what I mean by tied to the sun is that physically in space, it's between the orbit of Earth and the sun, which means that it's hard for it to be very far from the sun. It's not like Mars, where we can see it at midnight. We can never see Venus at midnight, just like we can never see Mercury at midnight. Okay? But we can see it in the evening and the early morning. Okay? And more so than Mercury, because it's first of all larger and brighter, because it's also very reflective, and we'll talk about that as a very reflective cloud layer, and it's closer. Okay? In fact, it has the special designation of being the brightest object in the sky other than the sun and the moon. Right? It's number three. Right? And it is really dramatic. When you see it in the evening or the morning, maybe right before sunrise, it really catches your attention. You think it's an airplane because it's just so bright, especially when its orbit is closest to ours. Okay? Okay. So the apparent brightness of Venus varies due to the changes in the phase and the distance from Earth. Okay, so Venus goes through a whole cycle of phases, just like Mercury does, which was part of the background of the heliocentric model and the realization that the sun and the planets do not orbit Earth because, as Galileo showed with early telescopes, the phases of Venus disprove that. And Venus's phases are famous for that reason, historically speaking. But we can certainly consider that when, excuse me, when Venus is in a full phase at a superior conjunction, it's quite far away, and therefore it's going to be dimmer due to its distance. But on the other hand, it's going to be very reflective because it has a whole surface that is reflecting the light of the sun. But when you have these phases of Venus where it is, say, a quarter phase, all right, at greatest elongation, this is a particularly bright time to see Venus because it's kind of a sweet spot between relatively short distance and lots of exposed reflective cloud layer. Okay, and of course the other example here is at inferior conjunction when Venus is between us and the sun. It's kind of like we're seeing a new Venus as compared to the new moon, in that we're really only seeing reflection around the edges of the planet. And although it's very close, it's just not reflecting that much light, so it wouldn't appear as bright in the sky. Now, seeing the actual circular shape of Venus like this really requires a good telescope. For most cases, it is simply a dot. Okay? And certainly to the naked eye observation, it's just a bright dot in the sky. Okay, so what are the physical properties, the details about Venus? Well, it has a radius of 6,000 kilometers, okay? That's very, very similar to Earth, okay? That's just a few hundred kilometers smaller than Earth, okay? So that's very close to the radius of Earth. Quite similar, okay? It has a mass that, again, is very close to the mass of Earth, okay? So it's kind of like our twin. Okay, its density is also similar to the density of Earth. Okay, it's variable, but this is the average density. I say it's variable because just like Earth, the core of Venus is denser than its outer layers. Okay, but this is similar to the density of Earth. All right. So really, the takeaway here is just how similar it is to Earth in its physical size. Okay, both radius and mass. Okay. And it's spherical, just like Earth. It's a terrestrial planet made of a lot of the same stuff, which the density is indicative of the fact that Venus is made of much of the same minerals, the same elements. But this is where the similarity stops, because there are some striking differences between Earth and Venus. And there's some things that really set Venus apart from all the other planets, from the 7 of the other 8 planets. And the biggest one of those is its incredibly long rotational period. Okay, its rotational period, okay, that's its sidereal day, is, well, I will get to its sidereal day, excuse me. Its rotational period is how long it takes to make a whole orbit around. I was thinking ahead, because the three things we're going to compare are going to be its rotational period, its sidereal day, and its solar day, okay? But its rotational period is how much time, excuse me, there we go, how much time it would take to make this full, nearly circular, because it's not very elliptical, orbit around the sun. Okay, that's Venus's orbit. That's how long it takes, 225 days. Okay, now the thing about that period is that it's going in the same direction as all the other planets, but it's spinning on its axis the opposite way. Okay, so if we look at everything in the solar system, 99% of it, from looking above the ecliptic plane, is going to be spinning counterclockwise. All the orbits are counterclockwise, and all of the rotations of the celestial bodies about their own axis are counterclockwise. Like Earth, for example, right? Earth is tilted a bit, right? But it's spinning counterclockwise about its own axis. There's its axis, okay? And it's orbiting the sun in a counterclockwise direction. All right. Now, there's another notable exception when we talk about the distant gas giants in terms of a moon, but in terms of the planets, Venus is the only one that actually spins on its own axis. I'm going to zoom in on this so we can see it. It's going to spin on its own axis in the clockwise direction. It actually rotates about its own axis clockwise, although it still orbits counterclockwise. Okay, so that is very strange. It's almost like it's upside down. Okay, like it has an axial tilt of 180 degrees. Or on the other hand, it's like it got turned back around. And the prevailing theory is that there was a huge impact with Venus early in its primordial protoplanet phase, just like Earth was impacted and created the moon. But the impact in Venus's case didn't leave a moon behind, because Venus has no moons, okay, no moons at all, but instead slowed its rotation, took away most of its rotational energy, and actually ended up pushing it the other way. So now it's very slowly rotating clockwise, whereas initially, due to just the way the formation of the solar system happened, there's really no prominent theory that suggests that it could have started rotating clockwise. It had to have started rotating counterclockwise, just like everything else. And it took some momentous collision to result in its current rotation. Okay, so rotating clockwise, only planet in the solar system. Okay, so that slow rotation, that retrograde, just means backwards, because the standard is, of course, counterclockwise, and it's clockwise, so we call it retrograde. But you can really just think of it as clockwise. Okay, as long as you view it from above the ecliptic plane. All right, but that retrograde rotation of Venus results in a large difference between the solar day, okay, 117, and the sidereal day. Okay, so what are the differences here between the days? Okay, so good reminder of what sidereal day and solar day is. The sidereal day is how long it takes to turn back around and get to the same position relative to the fixed background of stars. Okay, so it's like if you just look at the planet on its own, don't worry about its orbit around the sun, and have a planet, and you got some point, and you want to find that point to go all the way 360 degrees around relative to just the fixed background. In this case, the white page behind the picture I just drew. Okay, that's the sidereal day. Okay, so the sidereal day for Earth is about 4 minutes shorter than the solar day, because the solar day is how long it takes to turn around and have the same facing towards the sun. Okay, so that makes sense that for Earth, the solar day is a little bit longer, because Earth has orbited a bit and it has to turn a bit more to actually line itself up with the sun. We talked about this in an earlier lecture for an earlier chapter. Okay, in fact, I think it was chapter 1. All right, but the point is that because Venus rotates so slowly, the relative length between the solar day and the sidereal day are actually opposite. The solar day is much, much shorter, at only 117 Earth days, compared to the sidereal day, which takes 243 Earth days. Okay, and again, its orbital time is 225 days. So we see its sidereal day is actually longer than its orbit. All right, for the time it takes for it to go all the way back around is longer than its orbit. It's because, I mean, we think about like maybe two periods that are locked together. And we talked about that idea of tidal locking and synchronicity and this idea of resonance, okay? Well, the moon had that. If you recall, the moon has the period it takes for the moon to go all the way around orbiting Earth and the period it takes for the moon to rotate around its own axis. Those are about the same length, okay? But here we actually have, again, about the same length, but a significantly longer, by a few days, sidereal day compared to the year, the Venus year, right? So really, really unusual orbit here, okay? And by the way, the reason that the solar day is shorter than the sidereal day is well illustrated in this figure, where we can see by tracking the clockwise motion of this arrow here, we can see that it comes back around right here, all right? Or a good way to think about it is it actually, if we start here, this is day 0, okay? This is the way it's meant to go. I do it backwards sometimes. But here, if we start at this arrow and we follow this arrow after 39 days, and remember, it's going clockwise, okay? And then after 78 days, it's over here, right? Still, we haven't completed a solar day, but then we get back around, and here it is. Here's one solar day, okay? And one solar day occurs after 117 Earth days, okay? Not a full Venus year yet, certainly not a sidereal day, but just part of a full rotation. But now it's lined back up with the sun. It's lined back up with the sun because now it's on the other side. See, right? It's almost like it only had to do a half turn to line up back with the sun because in the meantime it turned so slow that the planet went to the other side of the solar system, right? At least the other side of its orbit around the sun, millions of miles, right, to go from there to there. Okay, all right. So there we have this very fascinating orbit of Venus. Okay, so long distance observations of Venus are incredibly difficult, and it's all because of the dense atmosphere and thick clouds. It's impossible to see through. All right, we can't look through the clouds of Venus with visible light at all. Okay, it's like trying to look through a wall with visible light. Okay, you can't do it. So that type of electromagnetic radiation is just not going to pass through something as dense as Venus's clouds, and much of its atmosphere for that matter, but certainly its upper cloud layer, way too dense. Okay. Now, because of that, we have to have clever ways of observing the surface, and we'll talk about how the surface has been observed. One way is with radio mapping, because very long wavelength rays, or long wavelength waves, light waves, can actually pass through, okay, the atmosphere. So you can send those low energy electromagnetic waves, radio waves, through the atmosphere, and then get some data off reflecting those radio waves off the surface. But since they're long, you don't get very detailed images, but you can see where mountains and craters are and so on, and volcanoes. There are a lot of volcanoes in Venus, okay? On Venus's surface, that is. You can try to get infrared, right, which is longer wavelength than visible light, but even that gets mostly absorbed because Venus's atmosphere, as we'll talk about in just a minute, is famous for absorbing infrared radiation. Okay, so it's very difficult. Radio waves are really going to be one of the ways that we can actually transmit through that atmosphere. Okay, the other way to get views underneath the cloud layer is to send a space probe down there to actually land on the surface of Venus. But the problem there is that the fact that the atmosphere has so many thick clouds means that it's like a blanket. And underneath those thick clouds, the temperature is 730 Kelvin. That's hotter than Mercury. That's higher than the melting point of low melting point metals, right? Silver melts at less than 730 Kelvin, right? So, I mean, it is so hot that it melts many metals. And so there's liquid molten, volcanoes on the surface because the surface is just so hot. So you can imagine then landing a space probe means you have to have a very, very sturdy space probe made out of very sturdy materials with high melting points. And even those don't last that long, okay? But that is a way to get some images of the surface. Okay, so probes flying near Venus, they can't really use much, to look. They can look deeper into the clouds with infrared, as I mentioned, and with ultraviolet, but they can't, even X-rays. They can try sending X-ray signals, but they really still can't see the surface. Okay, it's really just radio waves. So it's not just a limitation that that it's just observations based from Earth or from Earth orbit. Even near flybys are incredibly difficult, and that's so different than most planets, right? Because mostly in space exploration, if scientists can fly a probe past a planet, they can get really good images of the surface. Consider the recent flyby of Pluto. Okay, so there's so many good examples of that. Right, not a planetoid, not a true planet or a dwarf planet, but still, incredible, striking surface images. Okay, but not so with Venus. Venus is a tough nut to crack. There's so many mysteries about Venus because of that thick atmosphere. Okay. All right. So what do we know about the surface? Okay, through painstaking radio, signal collection and the few probes that have actually landed on the surface. Well, we know that it's relatively smooth. That's due to like the abundance of lava flows. Okay. There are two continent-like features, Ishtar Terra and Aphrodite Terra. Okay, so they're kind of like large continents surrounded by deeper kind of type of crust. Okay, so you have like kind of larger crust that sticks up and then deeper, flatter crust around it. No ocean, so they're not continents in the sense that they're surrounded by oceans at all. Certainly not. There's no liquid water on the surface of Venus. But they're continents in the sense that if you imagine, if you drained all the oceans on Earth, you could still tell what the continents are, because in between would be the big flat ocean basins. Okay. Now, another thing that makes them unlike continents on Earth is there's no plate tectonics, because on Earth, continents are often tied to plates and they move with the plates. Not so on Venus. Venus has a fixed crust. Okay, a big theory of the no plate tectonics is because there's no water. Because prevailing theories about what drives plate tectonics on Earth are our oceans. The oceans allow for the plate crust to sink down and then easily slide underneath the continental crust, and kind of continuing the whole process of energy that keeps plate tectonics moving. So without oceans, you can't have plate tectonics, at least as far as we know. Okay. There are mountains. Okay, so definitely there's volcanic activity that create mountains. So you can get mountains from volcanoes even without plate tectonics. There are craters, but not that many, because they tend to get covered over in lava because there's just so much volcanic activity and large lava flows. Okay. All right. So here is a mosaic of the surface of Venus. Okay, you can see kind of the flat parts on the back side of Venus, and on this side you can make out the continent shapes. Okay. Okay, here is a surface map of Venus. Now we can really see Ishtar, Ishtar and Aphrodite. Okay, the two continents that I mentioned, Terra Ishtar and Terra Aphrodite. Okay, right. So definitely, there could be an ocean in between, right? And maybe there was in the first billion years or so of Venus's life. Maybe there was an ocean, but it's long since gone. Okay. Ishtar Terra is one of two continent-sized features on the surface of Venus, right? You mentioned those, right? Taking a look at that continent, kind of seeing where it ends up, right? Big mountains and so on. Okay. The other is Aphrodite Terra. Here's looking at this continent here. Okay. All right. Lava has flowed from cracks on the surface, right? So there's large cracks where lava flows out of it. So we can see here an image of one of those cracks. See, look at these low-quality images, right? Because we have to piece them together with data from radio waves. Okay. Volcanoes on Venus, most are shield volcanoes. Shield volcanoes are indicative of very viscous lava, very low viscosity lava, so lava that flows like water. So it creates a big flat volcano rather than a high peaky one, because that requires very sticky lava, which is high viscosity lava. So the type of volcanoes are shield volcanoes. That kind of makes sense considering things are so hot. So that's going to cause the lava to flow more easily. Faster flowing lava creates these shield volcanoes. Okay, they can be very large, right? There's massive volcanoes. Okay. Other volcanic features on Venus are a bit more exotic. They're not just typical volcanoes. Although I'd say big cracks in the surface that have lava pouring out of them are pretty exotic. And these are lava domes. These are quite striking in this image, right? And this idea of coronae, they're unique to Venus. And essentially what they are, I have a better image here, is they're cases where lava has pushed up the crust, and then the lava underneath cools. And when that happens, that big piece of crust that was pushed up, kind of like imagine a cake that's rising in the oven but then cools too fast, what happens? The middle of the cake collapses. Okay, so as the middle of the cake collapses, it leaves a big collapsed center as that previous lava rise cools off. And that's what this looks like. Here's that collapsing center, and here this is the whole original formation that was pushed up from the lava, pushed up by the lava underneath the crust. Okay, because Venus does, as far as our measurements can tell, have a very thin crust, much thinner than Earth's crust, which is already pretty thin. What is interesting about these coronae is that they, again, they're unique to Venus, and for a long time they were mistaken for craters, because you could see, this circular formation looks like it's some sort of unusual crater, but in fact it's not at all. It's entirely a volcanic feature. Okay. So impact craters on Venus, they do exist, right? Here, they tend to get, affected by the weather, because there is sulfuric acid rain on Venus, and they also get affected by lava and volcanic activity. But we can still see some examples of these messy craters. Okay. All right, and we actually have some close-up images of the surface, right? We can actually see the rocks. It's unbelievable. Imagine that's over 700 degrees Kelvin or 700 Kelvin, right? But here it is, right? That's such heat, and these are taken by the Venera landers, which were a Russian space probe. Some of the only pictures of Venus's surface that have ever been collected. Okay, all right, so that incredible atmosphere that creates that heat, right, allows for all that volcanic activity, allows for such a hostile environment, just a absolutely hell in the solar system. What is it? What are the characteristics of the atmosphere? Well, it's very, very dense. It's about 21 times denser than Earth's atmosphere. Okay, it has a solid cloud bank about 50 to 70 kilometers above the surface. That's the one that just is not just completely can't be penetrated by visible light, can't see through it, right? The sulfuric acid cloud layer. Okay, a lot of sulfuric acid in the atmosphere. Okay, so there's sulfuric acid haze underneath that cloud layer. All right, there's a lot of carbon dioxide. We have that in our atmosphere as well. Okay, but that we do not have sulfuric acid clouds. Okay, because you know what's lacking in the atmosphere of Venus that we have in combination of carbon dioxide in our atmosphere? H2O, okay? We have a lot of H2O. We have H2O clouds. We have water clouds, okay? There is no H2O on Venus. And the idea is because this incredibly thick atmosphere has held in so much heat that there's enough energy in that heat, and, effectively from that heat, to break apart the H2O molecules, which allows the hydrogen to escape. Okay, because the hydrogen, now very tiny molecule or atom, right, or H2 being a diatomic molecule, is so light. It's the lightest thing out there. It's easily able to escape just from the energy, the thermal energy, and thus the thermal velocity is greater than the escape velocity. Those molecules are out of there. There's no hydrogen left. Okay, there's just not any hydrogen left in the atmosphere, right? And then the leftover oxygen is going to bond with the carbon and make even more carbon dioxide. Okay. So that's the point. We have an atmosphere that's devoid of hydrogen. Okay. So the upper atmosphere of Venus has very high winds. Okay, because there's probably that incredible amount of energy flow, right, from having so much heat underneath. But underneath that cloud layer, the winds are gone. It is still just dense, like just kind of stuck. Like imagine just like an oppressive atmosphere, just holding you in, like the hottest day, but then go 10 times hotter. All right, almost high humidity, but instead of water humidity, it's sulfuric acid humidity. That's what the surface is like. Still stagnant, pressurized air. All right, not breathable air at all, but air in the broad sense of a gas. There are also permanent vortices at the poles. As far as why, it's a mystery, right? Venus is full of mysteries, right? Just the fact that it's so hard to look at Venus, and it's just so strikingly unusual with that rotation and its high temperature. It is a planet of many mysteries. Okay, here's a little the description of this effect, this idea of having such a hot surface. It's considered a runaway greenhouse effect. Just like we have a greenhouse effect going on this planet, that has been dramatized by human activity. There's always been a greenhouse effect that makes the planet warmer than it would be without an atmosphere. That's because of the carbon dioxide and reflection of infrared light. But it's increasing. We have rising temperatures because of greater trapping of infrared light. Well, Venus traps much more infrared light than Earth currently does, much more. And that's the idea, is that effect has become so dramatic that if there was lots of liquid water at some point in Venus, that water was completely evaporated, which would have exacerbated, in other words, made the runaway greenhouse effect even worse. So that's why we call it a runaway, because it is a series of effects where one thing leads to another, and then that secondary effect makes the first effect stronger, right? Because once all the water starts evaporating, then you got even more oxygen to create even more carbon dioxide once the H2O has split from the oxygen in that process I described, because there's so much energy, okay? And furthermore, that as far as that splitting of the H2O in the atmosphere, right, the splitting apart and then the hydrogen leaving and then the oxygen becoming CO2, okay, and also then forming acids like sulfuric acid, that process not only being driven just by the high amount of energy, right, because the planet got hotter and hotter over hundreds of millions of years, but also because, and we'll talk about this in a minute, Venus has no magnetic field. So now there's another energy input that Earth doesn't have, which is all the solar radiation that gets redirected by our magnetic field, helps protect Earth from really harmful charged particles that are pushed away by the sun. Okay, those particles don't make it to Earth. They show up in the aurora borealis, the northern lights and the southern lights. Okay, but they don't affect our surface very much. They don't cause that huge amount of energy coming into our planet. But that does happen on Venus, and that would be so detrimental to having a stable atmosphere. Okay, you need a magnetic field to have a stable atmosphere. Now you might say, well, the atmosphere on Venus is stable, yes, but it is also oppressive, right? There's no way life can survive in these conditions, okay? And these diagrams, just compare, the case of Earth to the case of Venus, all right? And those incredibly high heats on the planet's surface, right? So much hotter, okay? So Venus's magnetic field, okay? There is no magnetic field, probably because its rotation is so slow. So that impact that slowed it down, that could have been the death knell of the planet. So imagine, there was some liquid oceans on Venus in its first billion years, huge impact, slowed down its rotation, its magnetic field faded over time, all that water evaporated, created the runaway greenhouse effect, and then incredibly dense, incredibly hostile environment that Venus now has. Okay, it could have been another Earth. Okay, there's no evidence for plate tectonics, and again, that the lack of liquid water on the surface is kind of part and parcel of that explanation. And absolutely, Venus resembles a young Earth. It got trapped in that 1 billion year phase because it never developed those full plate tectonics because it never developed oceans. Okay, all right. So in summary, Venus is never too far from the sun because it's between us and the sun. So it's that, just like Mercury, it's a morning star and evening star. Okay, star just being because it's a bright dot in the sky. Okay, the atmosphere is very dense, 21 times denser, lots of carbon dioxide. Okay, and then sulfuric acid rain as well as clouds. Okay, the surface is hidden by that cloud cover, right? Very, very few electromagnetic waves can pass that cloud cover. The surface temperature is about 730 Kelvin. Interesting thing, it doesn't vary. That's day and night. Okay, so it's the same temperature throughout because it's not driven by a day-night cycle with the sun. It's just the heat's trapped in there. Okay, it's an equilibrium and the heat's just trapped. Okay, the rotation is slow and retrograde as we talked about. Okay, possible explanation of early impact. Mini lava domes and shield volcanoes. Okay, so lots of volcanic activity. It's comparable to Earth in mass and radius, okay, as well as kind of internal structure as far as we know, okay? The large amount of carbon dioxide in the atmosphere and closest to the sun led it to a runaway greenhouse effect, okay? And that, that lack of magnetic field helped, okay? Absolutely. It could be close to the sun and have a strong magnetic field and be a very different planet, okay? All right, well, there we have it. Venus, another amazing part of the story of our solar system. I hope this lecture has been interesting and informative. Thank you so much for watching.